Okay, kids, I am on a roll today. Let's jump right into 4.3, derivatives and shapes of curves. Part 1, this baby one of, I'm thinking 3, this is a long section. So a couple of reminders going into this section. If a function's increasing on an interval, then its derivatives are positive. If a function's increasing as we go left to right, it's going up, so its derivatives are all going to be positive. If a function's decreasing on an interval, then its derivatives are going to be negative or less than 0 on that interval. So now remember, I know we could all pop things into our calculator and trace and do all that stuff, but using calculus, we're going to determine where this function is increasing and decreasing using, like I said, using calculus. We know that this is the graph of a quadratic function, a parabola. So it's going to be increasing from the vertex to the right and decreasing to the left of the vertex. We want to find that point precisely, not using the negative b over 2a because that only works for quadratic functions. We want to establish a process that's going to work for any function. So that being said, what we're going to do is determine where the derivative first is equal to 0 for this particular problem. So let's take a look at the derivative. So if f of x is equal to 3x squared minus 2x plus 4, then the derivative is 6x minus 2. We have to determine where the derivative, we have to find the critical numbers. Let me write that down. Find the critical numbers. So that's what I'm doing here. We'll set up this process formally momentarily. So I take the derivative, I determine where it's either 0 or undefined. This is a linear function. It's not undefined anywhere. So I'm just going to set it to see where it equals 0. So x is equal to 2/6 or 1/3. So this is my only critical number. So that is my only critical number for this particular function. So I know the vertex is going to occur at x equals 1/3 for my algebra days. So now let's take a look at this derivative. F of x is equal to 6x minus 2. If I look at a number line, here at x equals 1/3, the derivative is equal to 0, right? The derivative is equal to 0 at 1/3, and I'm going to look at the derivative to the right of 1/3. I'm going to look at the derivative to the left of 1/3. I can either do this algebraically, or I can graph. If we graph 6x minus 2, it crosses right here, and it looks like this, 1/3. So I can see from this picture to the right of 1/3, the derivative is positive. It falls above the x-axis, and to the left of 1/3, the derivative is negative. It falls below the x-axis. Algebraically, we can simply take any point to the right of 1/3, our favorite number to the right of 1/3. So I'm going to pick something simple like 1, and I'm going to stick it into the derivative. When I stick it into the derivative, I get 6 times 1 minus 2. I get 4. The output is 4. All I care about is if the output's positive or negative. I'm going to pick my favorite number to the right of 1/3. 0 is the simplest number to plug in. I plug in any number to the right of 1/3. I choose 0. I get 6 times 0 minus 2, which is negative 2. Negative 2, so the output is negative. So here, this is my only critical number. The derivative is 0. The derivative is completely negative no matter what number you chose to the left of 1/3. The output was going to be negative. No matter what number you chose to the right of 1/3, the output is going to be positive. So what can I conclude about my original function? Well, wherever a function's derivative is negative, the function is decreasing. Then it hits 0. Let's go back to our picture back here. So it's going to decrease. The derivative is going to be 0 right here, and then my function is going to increase. So that's going to be the point of my vertex. So then wherever derivative is positive, the function is increasing. So therefore, what was the, let me go back, I already forgot my question. It says, find the intervals where f of x is increasing and where it's decreasing. So we would conclude f is decreasing on, well, to the left of 1/3, that interval would be represented by negative infinity to 1/3, It is not decreasing at 1/3. It is neither increasing or decreasing, so we don't include that in our interval. And we can conclude that the original function is increasing. Well, to the right of 1/3, so we write the right of 1/3, 1/3 to infinity. And that would be the answer to that question. All right, so what we just did formally is called the first derivative test for functions. We use the first derivative to see whether the derivative is either 0 or undefined. We see how the function behaves before, between, and after any critical numbers, and then we can make conclusions about the original function. All right, so brace yourself. Here's the first derivative test formally. You can pause it and give yourself a minute to write this into your notebook or screenshot it, whatever works best for you. The first derivative test is used to find precise locations of all local max and min values. The first thing we do is find our critical numbers, remembering that the critical numbers for our function are where the derivative is 0 or where the derivative is undefined. So once you identify these values, I set up the number line and I look at what happens before, between, and after these critical numbers. If the derivative changes from positive to negative, so if the derivative changes, it goes positive and then it starts going negative. If it goes up and then it goes down, we must have a local maximum at that point. If the derivative changes from negative to positive, the function changes from decreasing to increasing, we must have a local min. Not all critical numbers give us local maxes or mins. If the derivative does not change sign at the critical number, then the critical number is neither a local maximum or local minimum. So again, take a minute, maybe pause the screen, write this down, and then let's apply it. Right, let's use the first derivative test to find all local extreme points for this function and determine where the function is increasing or decreasing. So the first thing we're going to do is find the critical numbers. So to find the critical numbers, we take the derivative. The derivative of 2x cubed minus 3x squared minus 72x plus 10 is 6x squared minus 6x minus 72. And we have to ask ourselves two questions. Where is this function equal to 0? And where is this function undefined? Well, the derivative is just a quadratic, so it's not undefined anywhere. So we're just going to set it equal to 0. You can use quadratic formula here, but if you think ahead, notice that all the coefficients have a common factor of 6. We can take this out. And notice what remains factors nicely. This is just x minus 4. X plus 3 equals 0, so we get x equals 4 is one of our critical numbers and negative 3. So therefore our critical numbers are just 4 and negative 3. So if this function changes directions from increasing to decreasing or decreasing to increasing, the only place it can do it is at 4 and negative 3. So I'm going to rewrite my derivative here. 6x squared minus 6x minus 72, and factored nicely, and this is going to become very useful. Right. Now remember, our concern is where this derivative is positive or negative. Wherever the derivative is positive, the original function will be increasing, and where the derivative is negative, the original function will be decreasing. The only place that this function is 0 is at 4. The derivative is 0 is at 4 and negative 3. So let me just stick this under here. We'll continue on with this. So my next step is to draw my number line. Just bring this down a little bit. All right, I'll get this eventually. There we go. That will work. Not exactly, but what I wanted, but. So we are going to draw a number line. This time we have two critical numbers. Make sure you put them in order on the number line. Negative 3 comes to the left of. All right. So we're going to see how the derivative behaves before, between, and after. The derivative is 0 at -3 and it's 0 at 4. It's the only place it's 0. And this function is a polynomial. It has no breaks or jumps. So it must be either completely positive or completely negative to the left before and between and after each of these numbers. So I pick my favorite number to the left of -3. Let's say -4, for example. So I'm just going to hypothetically stick in -4. Or quickly, I shouldn't say hypothetically, I'm actually going to stick it in. If I stick in -4, all I care about, the value is irrelevant. What is relevant is it positive or negative. So if I stick -4 in here, I get 6 times -8 times -1. And 6 times -8 times -1 produces a positive result. So all I care about is that between, or to the left of -3, the derivative is positive. So I'm going to pick my favorite number between -3 and 4. 0 is always a good choice. If I put 0 in, again, I'm only concerned about the sign of the derivative. So if I put 0 in the derivative, here it's at, you can put it either in here or here. I put it previously in the factored version because it was easier, but in either case, when I put it in here, I can see that I get 0, 0, -72. So the derivative is negative between -3 and 4. If I put it here, I get -4 times +3, still producing a negative result. So pick your favorite number to the right of 4. 5, for example. So I find it a lot easier to stick 5 into the factored version than to stick 5 into here and have to calculate that. Because if I stick 5 in here, I get 6 times 1 plus 8. Don't even care what it is, but I do care that the sign is positive. So I know the derivative is always positive to the left of -3. It's negative between -3 and 4, and it's positive to the right of 4. So now let's conclude how the original function behaves. The derivative is positive to the left of -3, the original function is increasing. Where the derivative is negative, thus in between -3 and 4, the original function is decreasing. And the derivative is positive to the right of 4, so then our function starts increasing again. So if a function increases and then it decreases, we must have a local maximum here. Local max at x equals -3. And if a function decreases and then it starts increasing, we have a local min at x equals 4. So therefore, we're going to conclude f of x, the original function, is increasing on, well, to the left of -3, so -infinity to -3, and to the right of 4, so 4 to infinity. It is not increasing at -3 and 4 because that's where the derivative is 0. And the function is decreasing on -3 to 4, so between -3 and 4. And then the question did ask a couple things. It says determine the intervals of increase and all local extreme points. So we have intervals of increase, intervals of decrease. Now be careful what the question is asking. In this case, we have a local maximum at x equals -3. The local max value, if it asks you for the maximum value, it wants you to put this point into the function. So it would be the function at -3. So value means output. And if we stick -3 into this function, I got 145. So you might just want to double check that. And then the local minimum would occur 4. So we have a local minimum value. To find the minimum value, we are going to stick 4 into the function to get the local minimum value. So it would be f of 4, and if I calculated it correctly, it's -198. Again, there's always the chance that I make a mistake. If I do, it's not intentional. Please, by all means, bring it to my attention, and I will be happy to fix it. All right, so I'm not sure what time I'm at, so I'm going to say to be continued. And I'll do a couple more examples in part 2. See ya.